In this video, we are treating radioactivity as a first order reaction. Remember, radioactivity is the spontaneous decay of unstable nuclei emitting energy in the form of radiations. And radioactivity follows the first order reaction, which is our activity equals to the decay constant times the rate at which reactant decay. In radioactivity, the decaying atom or the decaying nuclide is the reactant. So from this equation, we can have that our A now equals to activity, our lambda equals to decay constant, and our N equals to number of particles. If we measure rate in terms of the reactant, it will be negative. If we measure it in terms of the product, it will be positive. So in this case, we are measuring it in the terms of the reactant, which is our rate of reaction now equals to negative change in the number of particles over change in time, meaning as time progresses, the number of particles decreases, and this will be equal to our decay constant times our number of particles. In this case now, we are going to carry this negative sign over. We now have change in number of particles over change in time equals to minus decay constant times the number of particles. At this change, we are going to collect like terms. If you want to collect like terms, this equation will now result to change in number of particles over the actual number of particles equals to negative decay constant times change in time. So we are going to integrate this equation. We integrate the first side, giving it a limit, and integrate the second side. Now we now have integral of delta n over n equals to integral of minus decay constant times delta t. Having an upper limit n and a lower limit n naught. So now we now have integral. Our upper limit is n, our lower limit is n naught, delta n over n equals to, we factorize this whole thing, we now have minus decay constant integral of delta t. Integral upper limit as our n and lower limit is n naught. 1 over n delta n equals to minus lambda integral delta t. The integration of 1 over n is ln n. So now I have ln n now. Our upper limit is n, our lower limit is n naught equals to negative minus times lambda, the integral of theta t is t. If we substitute for our power and lower limit, we now have ln n minus ln n naught equals to minus lambda times time, such that ln n divided by n naught equals to lambda times time. So this will now give us n over n naught equals to exponent of negative lambda times time. That's our n equals to n naught times exponent of lambda time, where n equals to final number of particles. N naught equals to initial number of particles, or lambda equals to decay constant, and our t now is time. The formula can also be written as our activity equals to initial activity exponent of negative lambda t. Now the next step is to determine our half-life. Remember that the half-life of every substance is the time taken for a particular element to decay to half its original value. For half-life now, A now equals to A naught divided by 2. T is now T half-life. Substituting this to the equation now, we now have A naught divided by 2 equals to A naught times E minus lambda T half-life. Collecting like terms now, we now have A naught divided by 2 A naught equals to exponent now minus decay constant times half-life. This equation will now give us, after our A naught we cancel A naught, give us 1 over 2 equals to exponent of minus decay constant times T half-life. Let's take the natural logarithm of both sides of the equation. Now I have ln 1 over 2 equals to the ln in this side, we cancel the exponent on this side. Now I have ln the exponent of decay constant times half-life. So the ln will cancel out the exponent. We now have ln 1 over 2 now equals to minus lambda t half-life. Now in this case now, we are going to turn this division to subtraction. That's the rule of logarithm. When you have division in logarithm, that means you are subtracting. I say ln 1 minus ln 2 equals to negative lambda over t half-life. Ln 1 now equals to 0 minus ln 2 equals to negative lambda t half-life. You got to understand that our negative ln 2 equals to negative our decay constant, that is our half-life. This negative equals to this negative. We now have ln 2 equals to lambda times half-life. Half-life now will now be ln 2 over lambda, and lambda will still be what now? Ln 2 over what now? Our half-life. If you know how to derive it, you are at a better advantage. So let's summarize the whole formula that we have gotten so far. Our first formula was that activity equals to our decay constant times the number of particles. That was our first formula. Our second formula, we note that our N equals to, that is our number of mole that is remaining, equals to the initial number of mole exponent to the negative of what now? T, that is the time taken. And also our activity equals to our initial activity of the exponent to the negative of what now? Half-life times what? T of the time taken. The half-life now of a radioactive decay equals to ln 2 divided by the decay constant. And also we discovered that our decay constant now equals to ln 2 divided by the half-life. So these are the formula for radioactive calculations. If you want to calculate anything in radioactivity, you must know how to use this formula.